Welcome to this session at Voxxed Zurich. Great to be here and talk about big data analytics and machine learning and how bring that to real time. And I really think that's a real great combination, and that's what I want to talk today about. My name is Kai Wähner. I work for TIBCO, and we have middleware in the sector. So this talk is not a product pitch, but from the concepts and from the ideas behind that, we are doing exactly what I show you also with our customers, and we see that really in every industry right now. And that's also the motivation for this talk. The keyword or buzzword for that is digital transformation. So that really the physical and the digital world is merging. Now that everything has to be integrated, like we have seen in the Internet of Things talk, for example, before that. So that's really key, and also the motivation for this talk. And as you have maybe also seen in the keynote by Jonas Bohner, like he explained about historical data. So when something happened, then it's done, it's a fact, so you cannot change it. But nevertheless, you can store all of that, and later you can analyze it. And that's what we call typically big data. And you take a look at all the big data to find insights and pattern in that data. And when you have found these patterns and insights, then you want to bring them into real-time processing. That's also what Jonas mentioned in the keynote. He called it stream processing. So when you really process the data while it is in motion, so not first store it in the database, but really begin while it is in motion and act proactively to that. That's kindly the motivation of this talk, really use a lot of big data to find insights and then bring it into action in real time, what we call fast data. There's plenty of use cases. So as I said, we see that in every industry we have customers in, and it's about the window of opportunity, which is important for this part, where you can really analyze and act on critical moments while it happens, while the data is in motion. The window of opportunity might be just seconds. For example, if you have an optimized pricing engine to sell something or to check fraud before it happened, that's really the key. If you do just reports every hour or every night, then it's too late because the fraud already happened, or the customer is already gone out of the store, so you cannot do any cross-selling via some coupons or something like that in real time. So that's really, I think, use cases which are really with a short window of opportunity. After that, that's gone. There are other ones which are more about minutes, like rerouting transports, for example, in a logistic industry, or giving customer service, for example. There are also more long-running window of opportunities, for example, for predictive analytics, which is also really a key scenario we see more and more in manufacturing, in the automobile industry, and in engineering and all of that. There you have often 1 or 2 hours before you replace a machine, but still it's really predictive. You try to look into the future. That's also the use case which I will show you later in the live demo, how you can implement it from the beginning, from finding the insights and bringing that then into action, into real-time processing before it happens. And that's in the end really the use cases and the motivation why I do this talk today. And if you go out of this session in 40 minutes or so, hopefully you will still at least keep 3 key takeaways from me. The first one is that the insights are hidden in historical data on big data platforms, right? So no matter where you store in NoSQL databases or in Hadoop or in Spark or anywhere, in the end, that's the facts which Jonas mentioned in the keynote, and you store them, and you can store all of them in the meantime. It's not so expensive, and then you can find a lot of insights out of that data. And then you use machine learning and big data analytics to find the insights in this big data. And usually, in the meantime, you use analytic models for that. So it's not just the business user who takes a look at the data, but it's really the analytic models. And I will talk about what that means. And the third key takeaway is that then event processing, or as Jonas mentioned it in the keynote, as stream processing, that's then the way to use these models to take action in real time. And the key here also is you reuse these models, which the data scientists built for you, without building them again. So you really reuse them. I will also explain in more detail what that means. So with that, let's take a look at the agenda for the next 35 minutes or so. I will shortly explain what we understand under machine learning and big data analytics, because that's really key for the rest of the talk. And then I will show you all the steps necessary from finding the insights from the historical data, which is stored in Hadoop or another data store, and then to migrate it, let's say, these models to real-time processing to take action before something happened. And then at the end, I will also show you a short live demo that you get a little bit of feeling how that looks in the real world in a real project. Let's begin with the first one. What is machine learning and big data analytics? The very simple definition is that machine learning allows computers to find hidden insights without being explicitly programmed. Right? And that's really a key, because machine learning is used where you cannot easily implement the patterns and the insights. So usually a Java developer or so uses if and else and for loops and all that stuff to define the rules, what all the things which the program has to do. Right? For many applications that makes sense, but there are a lot of use cases in the meantime, especially with all this big data we have to analyze and use, where you cannot implement that. So let's give you a few examples about machine learning. That's the easiest way to understand it in the beginning. The first one is spam detection. We have this problem for many, many years, and it's still a very complex problem because it's not easy to find spam. You cannot implement it with if, else, and with for loops to define every spam by itself, right? So the machine has to learn what this is. And so it gets a lot of input, and from that it has to learn automatically to decide if something else is spam or not, even if it is not the same like the spam before. And usually also for this machine learning, it's the rule that you usually cannot decide it 100% sure. But if it's a good model, it can be 90% or 99%. Depending on the use case, you can define what is good. For spam detection, I would say maybe now we are at 95% or so. So it's working very well in the meantime. Other things are, for example, fraud detection, or another key, what we see more and more, if you read news about Google or Facebook and all of these, they are investing a lot of money into machine learning regarding digit recognition, so that you can read what someone has written with his hand, or speech understanding. Right? So, for example, this week I had to change my rental car for next week because I'm traveling another way. And I was talking to a woman, but the woman was a machine. And it talked to me, really. And it understood what I said. And depending on my answer, it told me what to do next. And so I had 10 steps or so, and she was talking with me. And this is a very good use case where you can see how much money every industry you can save with this machine learning, because in this rental car use case, you have a very nice woman who works 24/7 every week. She's always nice, and you have to buy her only once for some $1,000, right? So to compare this to the people which you have to use for that. And that's just one example where the businesses we see, they use it really because they can get a lot of business value out of it. You should not think so much about Facebook and Google with their face detection. I mean, they are also doing it for money, for advertisement and so on, but there are really business cases in every industry. So, for example, for product recommendations, if you think about Amazon, about Netflix and all that stuff, that's in the end machine learning. There are many, many other use cases. I will not go into too much detail here, but you will find it in every industry. So that's the use cases for machine learning. So there are a lot of different types which you can do with machine learning. I will only give a very short overview here and not go into details, just that you get a little bit of feeling again. This is really more the introduction session, I would say. And the first type you can use is classification. And usually the easiest way to think about machine learning is, again, by a use case which you think about. So classification means that the data is labeled, meaning it's assigned to a class. And here, for example, is it spam or is it no spam? That's the question for the machine learning model. Or another question, is it fraud or is it not fraud? So there comes an input into this model, and then you get an output. The output here is either it's spam or it's not spam. Another model is, you can use this regression, where the data is labeled with a real value. And for example, here you think about time series data, like the price of stock over time. And here often then you do not get a yes or no. So is it fraud or is it spam or so? But here it's usually about a probability. So for example, in predictive maintenance, which we will see later in the live demo, there you use the model to predict if the machine will break and explode. And depending on the percentage of the probability, you will make a decision, do I replace it before it explodes? Right? So it's never 100%, but if it will explode by 90% probability, then probably you will replace it before it explodes. Another type of machine learning problem is clustering. Clustering is not labeled, but that can be divided into groups. So for example, if you want to organize pictures by faces without names. So that's, we will see later in a little example, for example, the k-means clustering algorithm. So you put all your data in that algorithm or in that model, and then afterwards you get different clusters of answers in the end, which you can then use. For example, if you want to do a product recommendation machine learning with some input data, then you could, for example, get a cluster. One cluster is the man, one is the woman, and one is the children. And depending on that, you can make other product recommendations. And of course, it's much more complex, and you can do much more complex use cases and divide it into many more different clusters than these three as a simple example. And the fourth one, that's also a very interesting type of machine learning, that's rule extraction. So what does that mean? In the end, somehow, with some of the different models, there are so many models available for machine learning with different algorithms and so on. And with this, sometimes you just find a rule. You cannot explain it, all right? But nevertheless, it works for you. And so a key difference between machine learning and mathematics and statistics is that you do not prove a rule in the end. The mathematics always have to prove it. But with machine learning, you just try to understand the data and learn from it. It doesn't matter if there's a proof for that. So in this example here, we see that someone discovered, for example, in a store, that there is a relationship between the purchase of beer and diapers. What in the first thing doesn't make any sense, and maybe it does not make any sense at all. But nevertheless, it makes sense for this shop so that he sells the beer next to the diapers because they are sold more than, and you do cross-selling this way. So this is very interesting with these rules because you do not prove them, but nevertheless, it works for you. And so, as I see here on the right list, this is no complete list. There's a lot of different types of machine learning. And as I said, the easiest way is really to learn to it by taking a look at examples. But this is just to give you a feeling about what does machine learning mean. And now, the more interesting part is, what do you do with that? And that's so important because most companies do not do that. Again, it's not about Facebook or Google, but about the most enterprises we work with usually. And the key is that you do not just analyze and find a model. That's the first part. But then in the second part, you have to bring this model into action, to act in real time with this model before the fraud happened, before the customer left the store because you cannot do cross-selling, before the machine exploded, that you can replace it. That's really the closed loop for big data analytics, which we see. And afterwards, it goes back. So after you have implemented it, you have to revalidate the model, maybe create a better model, or maybe the circumstances changed. So you always have to do this loop to have the best result of your machine learning implementation. And for this, in the end, we have now 3 steps. We call that the analytics maturity model. And I will go through this very quickly because we see that picture more and more in the talk in each section. So first, we do self-service dashboards. That's really the business user. So he does measurements and diagnosis of historical data. He takes a look, he does visualization, and he maybe finds some insights with some problems and so on. But then the value to the organization, which here you have some immediate value, but the real big value is then if you go to the next step and get help by a data scientist. So that is really an expert with mathematics and also with the industry you're in. And he can take all the historical data to build a model for predictive and prescriptive analytics. So that you can use the historical data to take a look into the future with a certain probability, of course. But it usually works with, I would say, 90%, 95%. And in many use cases, this is a very good prediction for doing cross-selling or fraud protection or so. And then the third part then is the event processing, or like in the keynote, stream processing, where you really act on new events. Based on historical data, you found the insights, and you bring that into action in real time for new events. Right? That's the 3 parts, which we will talk about more in the next 2 sections. So let's first think about the historical data. So it's really here 2 parts. First, you have the historical data. You find your patterns and insights, and afterwards you bring it to action. The analytics pipeline typically has 5 parts if you describe it on a hype level. It's data acquisition, data munching, the data analysis, and then you build the model and validate the model. That's really the part of the business user and the data scientist together to build the model. So here again, we are in the first part of our maturity model. Now here, the business user starts with that. And first, he does the data acquisition. So before you can do all what you see today, you have to store the data. So that's the first issue. We have many customers which just now understand that they really have to store data from everywhere, because only then you get the benefits out of it. Usually you find only insights if you combine different data from different data sources, which might be stored in Excel sheets or maybe in a big data cluster like Hadoop or wherever. In the end, you have to get all this data in, either with coding or with a tool where you can do that graphically, but that's the way to get access to all the data. In the second part, you do the data munching. Munching is an English term. It also means wrangling or mash up. So that's maybe the best to describe this. And to show you an example how you do data munching, in this case you have input where you have departments. In this retailer, for example, with C, A, and B. And what the business user or data scientist wants is another table where you have a column for each of these departments to analyze each column by itself. And that's basically data munching, that you really get out of the input data, the data in a structure which you can reuse for building your model. And in almost all use cases, this data which you use in the end is just flat files. So almost in all use cases, really the data scientists need flat files for their data instead of XML sheets or whatever. In the end, they need something like this so that they can build their models out of that. After you have done that, then you come to the exploratory data analysis. That in the end means, if you take a look at Wikipedia, simply you use it to analyze data sets, to summarize their main characteristics. And often, and that's very important already, with visual methods. Because for a human, we are no machine, we cannot do machine learning by ourselves. And for us, it's much easier to use visualization. If you take a look at a little bit more complex definition of this term, then you see here it's used to maximize the insights into our data set, and you uncover the underlying structure, and so on and so on. So what's really the key of this part of the data analysis in the end, nevertheless? And that's a statement from 1977, so it has nothing to do with the modern data analysis we do now with big data. But it's that the greatest value of a picture is when it forces us to notice what we never expected to see. And that's really the key of the whole historical analysis. You usually take a look at all the big data in Hadoop or somewhere else to find insights which you did not know before, because that's the way why you do it, and that you can implement then into a model to bring it into action in real time later. And for that, you usually should use a visual analytics tool which can help you here. Some of these tools are interactive brush linked. That means that if you have different visualizations of the same data, if you, for example, select here just 2 lines, then all the other visualizations are also updated with that. And in this way, it's very easy for the business user to find insights which you did not know before. And that's really the typical scenario how you do it when you want to find insights which are not known yet. So that's the part of which the business user can do by itself. But then with all this big data, what we usually need in the meantime is really the models for predictive and prescriptive analytics, so that you can really take a look into the future and not just at the past. Here, in the first one, you can find the problems in the past. But here, you then can predict how will it be for future events, right? With an existing probability, of course. And therefore, the next step in the analytical pipeline, and this usually can only be done by a data scientist, which can program and understand statistics and mathematics, and also understands the business domain, then he can build a model with that. And what is a model? If you take a look at this picture here, so what do you see here? You see here a boat, a model of a boat, and you see here a picture which is made by a photo for a boat. So in the end, both are models, and the key is that a model is a simplification of the truth that helps you with decision making. And that's exactly what you do with machine learning and with these analytics models. You build a simplification of the truth, which helps you with decision making. Usually, for example, by calculating a probability, if it is fraud, if the machine will break, or something like this. These kind of models, it's usually a formula or something like this. Often it's very, very complex. And well, this is again some parts of the data scientists, which I am not. So in the projects we do at customers, I also have colleagues which help me with that part, finding the data model, and I can then bring that into action later with our tooling. And there are different parts. It's, for example, supervised models. That mean that you already know what you want to get. So, for example, is it spam? Is it no spam? Or to find out a specific probability of a problem. The unsupervised model, for example, again with the clustering, that means you do not even know what you will get out of this machine learning. So you really run different machine learning models and get out some information you do not really know before what you will get. But maybe it's some insights which you can reuse. And so what the data scientist is doing, he's using several different algorithms and building several different models until he finds a model which works for his use case. Typically, after they have a lot of experience, they find it easier because there are so many different algorithms, but they get a feeling when they take a look at the data to think what makes most sense. But nevertheless, they build a lot of different models before they find one which we really bring into action because it makes sense. Let's take a look at one example for model building. So this is one graphic which has two parts. The x-axis is the emails and employee rights, and the y-axis is the salary of this employee. And if you just have these two information and think about it, and that's the formula for that, then you could think that, well, that's great, because employees who write longer emails earn higher salaries, right? So that's when you take a first look at this model. So you could imagine that this model is wrong. So data scientists always have to improve their models. And for example, by adding a second data set or information, it's just one information in the end. And in this case, the information is that the blue ones are the employees and that the other ones are the managers. And after that, the data scientists can calculate a new model which shows it in a better way. And here now you see that based on this model, which is still very simple and might not be 100% true, but it makes much more sense than the first model. And here you see that the managers usually earn much more money than the employees. And for the staff, you all see that if they write more emails, it's even going down. So if you write too many emails as an employee, you earn less money, right? And this is just an example of how you build a model and how to improve it. This is still not finalized probably, but it's a better model than the first one. And then after you have such a model, you have to validate it. So the basic idea usually also is that you do not use all your existing data for building a model. So for example, you only build a model with 90% of the data, and then you evaluate it with the other 10%. So the formula which worked for you for 90%, try it out with the other 10%, and then you find out what's really true. Does this model work or not? In this case, for example, they are validating a model for how is the IQ of a kid related to the IQ of his or her mom. And here, probably you can read it, but you simply see here that some attributes are relevant here. For example, if the mother was at a high school or was not at school, for example. So, and there are some other parts. So, for example, if she's black or white, that doesn't matter for that, for the IQ. And this way you do model validation and understand which attributes are important for your model and which are not. Or even which influence it in a wrong way. That can also happen. So that's basically the analytic model we built with these 5 steps. And now let's also take a short look at the technologies behind that. So data scientists use a lot of low-level technology, I would say, like SQL, or in the meantime, a lot of Python and R. These are probably the 2 most important languages which data scientists use. On top of that, there's a lot of different tools. I will not go into detail here, but just to give you an overview, there is the coding tools where you have just languages like R and Python, as I said, the most important ones. You have open source frameworks like Apache Spark or H2O. You have products like TIBCO Spotfire, SAS, or IBM SPSS. And in the meantime, also the cloud providers have some offerings, like Amazon's machine learning, the same from Azure and from IBM Watson. So everybody has something here for data scientists. I will take a look at a few of them to give you a better overview. The first one, and that's really the most important language right now for doing machine learning in the understanding of the analysts and of the, if you do global Google and all that stuff, that R is really the most increasing one for that. Because for one reason it's open source and everybody can use it, and you do not have to pay money for it like for other vendors tools like SAS or something like this, and some other reasons. On top of that, you can also use different solutions. For example, you can use Revolution Analytics, which was acquired by Microsoft a few months ago. Here then, you have still the open source version of R, which by the way is GPL license. And that's not so good for this part, because then if you build a model under GPL license, if you use the open source solution, you have to also publish this one. And so if you use machine learning for getting insights and so on, you probably do not want to publish this to your competition. And so, for example, we with TIBCO and some others have gone another way. We built our own R engine. This is really our own code, and it nevertheless executes the same R code. So you can still build it with the open source, but run it in this engine. And but this has no license issue. So here you can build it and do not have to publish it to the competition. But let's not go into much detail more here. There's also an interesting article by Forbes which explained the difference, because I think it's important to understand the difference between open source R and the normal R and the other R. The second one, Apache Spark, only again very short. Apache Spark is a general data processing framework, but they really focus on analytics. So most times I have seen Apache Spark right now, and also if you take a look at the web at different analysts, usually they use it for Spark SQL and MLlib, which is their machine learning library. That's really the key usually which you use, where they have implementations for different machine learning algorithms behind that. Another one we see more and more at customers is H2O. H2O is also open source and uses a lot of different open source technologies. And as you see here, under the hood, it can run on Hadoop and on Spark. So you leverage all your Hadoop solutions or open source solutions you already have, and H2O on top helps you building the machine learning models. One of the benefits of this one is that it has very good performance when you want to score the model in real time then. And also for the evaluation, you can do it in a distributed way when you want to build the model. So here, for example, R has the disadvantage that it's very slow and you cannot scale it easily. And therefore, many are going to other solutions. So I think the key here to remember is that there's a lot of different frameworks available for building models, and for depending use cases, this is one is better or the other one is better. You should not think just about one framework for this model building part. Okay, but it's not just about model building, and that's important, because the data scientist can build a model, but nevertheless, the business user should also be allowed to use that. And therefore, with tools like TIBCO Spotfire or others, you can do data discovery very easily with visual tools, and you can not just analyze the data like I explained in the beginning, but you can also bring in the analytic models which you have built. So in this example, I have one where you use Spotfire together with R. You can also use it together with H2O or Spark or whatever you integrate into your tooling or what the tool supports to integrate. And in this case, it's about customer churn with the random forest machine learning algorithm, which is again one of the 200 algorithms available or so. And the benefit here is that the business user can use the model, and once it was imported, so the data scientist built it outside and imports it, and then every business user can use the model. And here in this case, you just have to select from this box here the attributes you want to use, and then you click refresh, and then it uses the model in the background to calculate that. Now that's the separation of concerns. One of the reasons is that not many people are data scientists, and there are not many available in the market, and the business user also find the information in their business much easier often. And so it's important to combine both the business user with a tool like Spotfire and the data scientists with R or SAS or whatever they use. And yeah, therefore, you have here the example with selecting, as I said, the variables for the model. That can be done by the business user. I already mentioned it, the SAS machine learning, they also have different models. Let's not go into too much detail. And there's also a standard for predictive model markup language, which is called PMML, predictive model markup language. This can be used, for example, you implement a model with one vendor like SAS, and you implement that, you use that into the stream processing solution of TIBCO, for example. So this was the analytical part, to find the patterns by the business users and by the data scientists. And now let's come to the important point, because without this, you do not have any business value by finding the model. You can do something manually, some decisions maybe, but the key really now comes by bringing this into action. And that's the third part. So here we're talking about streaming analytics or stream processing, or whatever you want to use the term. Event processing is another one. The key is that you get all the data in and you monitor that all the time while the data is in motion and can act proactively on that. You can do that with machine-to-machine communication, automation, so making decision by the computer, or you can use something where you get the data live to the UI, where the human can still make the final decision on that. There's again a lot of different solutions available on the market. I will not go into too much detail. Just again as overview, there's open source solutions like Apache Storm or Spark Streaming or Apache Flink. On the other side, you have the vendors like TIBCO with StreamBase, like IBM with IBM InfoSphere Streams, or Software AG with Apache. And again, you also have the cloud providers. So Amazon has a stream processing framework which is called Kinesis. I will not go into detail here. I had a talk about this at Java 1 in San Francisco last year. So if you want to understand the comparison between open source and the product and SaaS and so on in more detail, you can just go to my blog or to SlideShare, and you find a very detailed comparison of all these different frameworks. The concepts behind all of them are the same in the end. You want to bring something into action and process while the data is in motion. In this case, and on the live demo, I of course use TIBCO StreamBase, which is our product. But as I said, the concepts are the same. You get streaming input in real time, and then you do things like aggregation and filtering and integrating models and so on, and then sending an output somewhere else. And on top of that, what we at TIBCO call live data mart is that you have also a real-time UI for that. And the important thing is here, you cannot just monitor the stuff in real time, so the events are pushed to that, but you can also take actions on that. Whatever you have defined or whatever makes sense for your use case. In the predictive analytics, for example, for replacing a machine which will probably explode, you could take a look again and then send an email to the operator or stop the machine here directly by a right click and say, stop this machine because otherwise it will explode, or anything like this. The important thing here is that many things should not be completely automated. So often it makes more sense if a human has the last decision. And that's a reason why most of our customers also use the real-time view and actioning for humans in combination with the automatic stream processing. And now we come to the key part, which is now the question, how to apply analytic models to real-time processing. And the key here again is without rebuilding it, because that's the key advantage which you want to do. And you can do that with stream processing. So with a tool like TIBCO StreamBase or probably also some others, you can take the models which you already built with an analytics tool, and then you bring that model into action without rebuilding it, really by just using the same model. And I will give you a short example now and also show it in the live demo for a minute. So here we have an example where we use TIBCO StreamBase together with R. So here we have an input. It's a very simple process, right? So it's really just showing the activity of the integration of the analytic model. But here you get an input, and for example, from a machine, a sensor machine, or from the customer which walks through the store via an iBeacon which sends a message or something like this. And for every single event, you do a score. A score means using this analytic model and act on this real-time event. So you have used hundreds of megabytes or gigabytes of terabytes to build the model first of the historical data. And here now you bring it into action to do predictive things. Before the fraud happened, before the customer left the store, before the machine breaks. And this was one example with R. Another one is then with H2O, for example. And you see here, you do not rebuild the model. So you use the model which the data scientist has built and also which the business user has used in Spotfire in our case. And the same model without changes can be deployed to StreamBase to execute it in real time. And by the way, you can, of course, also later update and improve the model and deploy it without redeploying this application. And for another example here is with the PMML connector. And in this way, for example, we can also integrate solutions by other vendors. So if a customer already has SAS, for example, which is a proprietary solution for analytics, but they do not really have real-time processing solution, at least not a really, let's say, performant one, then you could still export the PMML model from SAS or another vendor and import it to StreamBase and execute it here. And here you see the PMML is in the end, it's XML-based, so it's really a standard-based model. This is a more real-world application that you see. The scoring, in this case with PMML, is just a small part of the whole stream processing application. Right? I will not go into detail here, it's just to give you a little bit of feeling about the complete story and also the tooling. And therefore, let's take a look at the live demo, which I want to show you for a few minutes, so that you get even a little bit better feeling about the tooling and how that looks like. In this live demo, I used the scenario of the predictive analytics of, in this case, from a customer from an oil platform, which has, as you can imagine, a lot of sensors. And they came to us, I think it was 2 years ago, and said an outage on a well can cost 10 million per hour, and they have 20 to 100 outages per year. So that's a real business case, isn't it? And if you think about this business case here, and now what they did, they implemented exactly this closed loop with us. So first, they understood the historical data which is stored in Hadoop. There are terabytes of data of so many different sensors. And then you anticipate this data and you build your model and bring the model into action in real time. And you still later improve the model, you go back, and that's a closed loop. But really the key is that the sensors are processed and in real time, that you can do predictive maintenance with all the tooling here, as you see on the screenshots. And let's give you some more details before switching to the live demo. Here you see just one of these examples with a lot of different sensors. So there's a lot of different data which is created every second, and you have to store it to analyze it later, from the pump and the protector and the ESP motor and so on. And the goal is afterwards that you have these different data. Here, of course, it's a simplified example, but here you have a voltage sensor, a temperature, and a vibration sensor, and all of these are creating streaming events in real time. And what you see here is the insight which we had from the historical analysis. It's a pattern which is defined in this streaming rule, and only when this pattern acts within a specific time frame, a sliding window in real time, then you have to send out an alert to maybe replace the machine, because then it might explode, and this costs you 10 million, as we have seen. If you replace it, it costs only 100,000. And so you have to think about it. It's a 90% probability. Then let's better replace it, even if it's not 100% sure that it will break. And from the architecture perspective, in the end, as you see here, you have the machine data which sends all the data. You also integrate it with other systems, like an ERP system in this basic example, to have transaction history or production volume or so. And you bring all of that to the historical analysis to find the patterns or to create the analytic models. And then you deploy that into real-time processing to take the action, to stop the machine and to send the mechanic before it breaks and explodes. Behind that, you see the basic architecture, and that's independent of the technology you use under the hood, if it's open source frameworks or products like TIBCO. In the end, you have two key parts for this story. The first one is the analytics part, where you have a data storage, like Hadoop, like data warehouse, like Oracle, like NoSQL, whatever. And you have analysis tools. Here you have things like TIBCO Spotfire, where you can do visualization by the business user, but also integrate and build all the models with R, with H2O, with Spark, MLlib, and whatever will come in the next years. We never know. And then we bring that into action, and that's the real-time component. In our case, of course, it's TIBCO StreamBase and the TIBCO Live Data Mart for the real-time processing and for the human interaction. Here, of course, you could also use something else like Apache Storm or Apache Flink and build your own web UI with JavaScript. That's always a trade-off between, of course, the open source and the vendors and all that stuff, pros and cons. But that's basically the idea. You have the analytics part and you have the event processing real-time part. And so I have just a few screenshots. It's more or less for reference for later if someone wants to see it again. So let's go to the live demo. Let's go over these slides and go to the live demo. And here I will show exactly how my colleagues implemented that. So what you now see is an implementation of a proof of concept for this customer before they decided to buy the product. That's typically what we have to do at a customer or at a prospect. And I will show you 3 things here. The first thing is, in this case, TIBCO Spotfire. TIBCO Spotfire, that's the tool to do the visualization, and the business user starts with that. He gets the input data from Hadoop or from somewhere else and creates different visualizations which interests him and where he can understand and maybe already find problems before he works with the data scientist together. So I don't understand too many details here, but again, that's an expert of this business case or industry. And after that, that's the business user. That's the first part of the 3 steps, right? But then the data scientists come in because he has to build the analytic model, which then can be used to find the problems and insights and bring that into action later. And therefore, in this example, we use R. So again, it doesn't matter if it's R or Spark, MLlib or H2O or whatever. In this case, it's R. And so the data scientist maybe uses just the R Studio, which is an open source IDE for Spark, where you can execute code and play around easily with it. That's really low-level coding in the end for a method, for one who understands mathematics and algorithms and so on. And here, he can already build a model, like, for example, or use a model, which is now let's say it correctly. He uses an algorithm to build the model. So the final model is used by using the algorithm, combining it with the training data, and then you build the model. And then when you have built a model, then you can use it in the next step, here in this case, to predict about new data. So the existing data has already some probability for, in this case it's now churn, or if it's the machine, the predictive analytics, it's the probability of a machine breaks. And then you predict it for new data where you do not know it because it's coming in real time. And therefore, when building this model, you have to split it, as I said. For example, you use 90% to build the model, and then you use 10% of the data to predict it, to validate it. And when you have a model which works to you, then you can store this model. In this case, it's an R model. You can store this. In this case, it's stored to a file here. So here you see the model is fit.rdata. rdata is a data type for R. And let's open this in a R console. And here now you see the model is named fit. That's in the end an R object. And here you see the model of the object. I have, in the end, no real idea what it is doing, and I don't care because that's done by the data scientist. He builds the model once, and then all the business users can use it to find and improve everything, and you can also use it to bring it into action. So let's first show you the Spotfire part again. So here we have already our model, our R model integrated into this. So for example, if you now change this leg here, each time you change it, it recalculates all this visualization using the model in the background, which there are so many options you have. For example, you have out-of-the-box support for k-means clustering and many others. And you can also integrate your custom models. So here you see data functions. And here you see the different ones. And here it's just some simple R code which calls the model, right? So let's see one, for example. This is just one which calls the model in the end. And in this model, what's happening here, or in this scenario, in this case, you see the different sensors which are creating data, and you see the outliners and so on. And in this case, it means everywhere where you see this black one, here it's an outage. Here the machine breaks, right? And in this case, it's not 100% true, because here you see one where it's broken, but not after this pattern. So you see the probability is not 100%, but it's a very good model, as you see here already. And therefore, that's the Spotfire part. But now for the last thing of today, how to take this into action. Now let's go to TIBCO StreamBase. I will just start it before I start talking about the example. What we have here, in the end, is one of the implementations. I will not go into much detail here, just that you get a feeling about that. You have different inputs and different components which you use, and here you can either build the rules by yourself, graphically and by configuration. So for example, in this case, we have defined a dimension, a sliding window, which it is called in stream processing. You can define the aggregate functions and the group options and so on. That's when you build your own model in the tooling, right? Often, if it's a simple model, that's fine. If it's a more complicated one, and here I have the example where we use the R adapter, and here you see we have our input, and then we have our R component to do the score. So for every event, you do the score in real time, and then you process it. For example, you send the alert to the live UI. And here you see the model here is exactly the fit.r data, which is reused and was before built by the data scientist. So that's the basics here. So let's see if my machine started to also show you the live UI for a minute. Because as I said here, it's important in this case, if such an alert is created, because the replacement of a machine still is 100,000. You can save 10 million, but 100,000 is still a lot. And therefore, you have the live UI here, where you see all events in real time pushed. And you see some red. Here it's a simulation which is running fast, so it's faster than usual. And then the business expert can take a look at that and also take a look at the historical data, and then he can make a decision, yes, let's really replace it. Or in this case here, there's also actions configured, and one could be, for example, stop the machine because it's probably breaking soon. That's basically the live demo, and so let's conclude. If you see the slides in the right way, let's try it here one more, presenter view. Yeah, if you go away with 3 key takeaways, the first one, insights are hidden in historical data on the big data platforms. Before you do all the other stuff, you have to store your data first, your big data, everything as much as you can, and combine the different data sources to find the insights. Machine learning and big data analytics find these insights by building analytic models. It doesn't matter which technology, if it's R or SAS or whatever, and it will be more in the future. We will see new frameworks, so everything has to be supported, right, without rebuilding. And you have to also then be able to integrate that model into event processing or stream processing, and there you can use these models without rebuilding to take action in real time on that data. And that's it. Time for questions? 2 minutes for questions. I think 2 questions or so. I don't see anything, so.
Hi. If I understood you correctly, the model contains the information how all the variables correlate with each other. And
sorry, I don't hear you.
Better now?
Now it's better, yeah?
If I understood you correctly, the model contains the information how the variables correlate to each other and when something should be triggered or not, or how it should be classified. Now, if the machine, or if an event happens, something external, for instance, you see in Germany that now parents of teenagers start buying tennis rackets because they have a new Grand Slam victor. Is the model able to adjust itself, or does in the end some user be the one to adjust the model that we now I don't know, cross-sell tennis rackets to parents?
So in the end, I'm not sure if I understand everything because the sound was not so good, but in the end, what does the model contain? I mean, that really depends on how you trained it and what you trained it. The basic is that you have some inputs for the model, and then you have to define somehow, of course, that it learns in somehow or the other how you train the model, and then the model is executed on that. Okay. Maybe we can discuss it afterwards because maybe one more, or maybe the other one's also here because, as I said, I didn't really hear it. So I hope you learned a lot of it, and also later come back to me via email or contact me if you have some questions, and thanks a lot.